So this is what the setup would be. So it gets back to our synthetic division dividing polynomials that we started on Friday. So is it actually a factor? Meaning, can I take x plus 4 times something and get right back to this 3x to the fourth minus 48x squared plus 8x plus 32? If it is a factor, this will be true. I can take this binomial times something, and I can rebuild my initial polynomial. Okay? The factor theorem says that if x plus 4 is a factor, if and only if f of negative 4 equals 0, meaning if we put in negative 4 into this, if we put negative 4 back into our original function and we get 0 as an answer, then yes, x plus 4 is a factor. But pay attention to signs on here. Okay, so this is x plus 4, but it's saying f of negative 4. So this gets back to synthetic division, the press box, all that stuff. Then we actually put the opposite in our press box, and this is saying that negative 4 is a 0. So then if we were to build a polynomial, it would look like x plus 4. So negative 4 being a 0, meaning it's going to cross the x-axis at negative 4. But if we were to rebuild as a polynomial, it would be x plus 4. Okay, so this is how we can check. So this is the factor theorem. In algebra 2, we talked about this as the remainder theorem. Okay, it's all the same thing. If I have a remainder of 0, then yes, it has to be a factor. Okay, let's look at this one. So we have some function x to the fifth plus 6x to the fourth, 11x cubed, 12x to the fifth plus 5x minus 20. Is x plus 4 a factor? Okay, let's actually work this one all the way out, and let's figure out what that other one is. So x plus 4 times something has to equal this x plus 5, that big long polynomial. So to figure out that something, we need to do our synthetic division. So with our synthetic division, what am I going to put in our press box? If x plus 4 is going to be a potential factor, my press box, I would actually put negative 4. And then I'm only looking at coefficients for synthetic division. And so this would be 1x to the fifth, 6x to the fourth, 11x cubed, 12x squared, 5, negative 20. Okay. How do I do synthetic division again? What's my first step I'm going to do from here? Okay, the 1 comes down, and so this becomes 1 times my press box to get negative 4. And then remember, we are adding as we go vertically with synthetic division. So 6 plus a negative 4 is going to be negative 2. Or I'm sorry, positive 2, not negative 2. Positive 2. Okay, and then as we keep going, 2 times a negative 4 would be a negative 8. Add these together, I end up with positive 3. This becomes negative 12. 12 plus a negative 12 gets me 0, but that 0 is important. It's going to be a placeholder. 0 times negative 4 is 0. Add these together, end up with 5. 5 times a negative 4 is a negative 20. Add these together, I get negative 40. Again, this is the remainder. Factors do not have remainders. Okay, because this is not 0, I would say x plus 4 is not a factor of, I'm just going to write f of x. I'm not going to write that all out completely. So when we do this synthetic division, this remainder is important. If we get a remainder of 0, then yes, it is a factor. But if we do not get a remainder of 0, then it is not a factor. Another way to check this is the remainder theorem or the factor theorem says if I put in negative 4 into this, so negative 4 to the 5th plus 6 times negative 4 to the 4th plus 11 times negative 4 cubed plus 12 times negative 4 squared plus 5 times negative 4 minus 20. Yuck, it's long. But I put in negative 4 to all of that. Any guesses what the answer is going to be? 40. Negative 40 specifically. Okay, this is the factor theorem, also called remainder theorem from algebra 2. That says if I put all that in, I get what the remainder is. So now synthetic division, though, you can't overlook this because this would build the second half of the polynomial to complete everything, quotient, divisor, all that stuff. But in terms of is it actually a factor? It is not a factor because we have a remainder, and also by remainder theorem, if we plug that in, we would get a number that's not 0. If it's 0, it's a factor. If it's not 0, not a factor. Okay, so you did this in algebra 2, so here's kind of a quick refresher on it. All right, let's take a look at another one. I want to actually factor this polynomial into linear factors, and given that 5 is a 0. So what that's saying is f of 5, if I were to put 5 in here, I would end up with 0. So if I did 6 times 5 cubed minus 37 times 5 squared, if I listed that all out, I would get 0. And they're telling me, given that 5 is a 0. Okay, since they tell me 5 is a 0, x minus 5 is a factor. Again, 5 being a 0, meaning that it's going to cross somewhere here at 5. And so if I have some function that's crossing here at 5, I can write this, if I factored out, it would look like x minus 5. Okay, so to confirm this, we have to do our long division or synthetic division to come up with the additional factors. Okay, because it's x cubed, 6x cubed, I know there's going to be 3 that multiply to get my function. And I know one of them is x minus 5. I need to come up with the other 2. Only way to do that is with division. So what's going to go up here in my press box? Positive or negative 5? Positive 5. All right, so now I can just put in my numerical values, my coefficients. So 6, negative 37, 32, and 15. And do not forget, if there wasn't, say, 37x squared, if it was 6x cubed, and then went right on to 32x plus 15, I would have to put a 0 in there for negative 37. That placeholder is important. All right, so let's do our synthetic division. So I'm going to bring down the 6, becomes 30. And again, remember, we are adding. So this becomes 7 after I add those together. 35. There we go. I was going to say something's not right there. There we go. Negative 7. Negative 35. So that becomes negative 3. Negative 15 gets 0, which kind of confirms this is a step along the way. I'm getting 0 for a remainder, so yes, x minus 5 is a factor. They already told me that, but I just confirmed it. But this other 6, negative 7, negative 3 is important. This is always that constant, and so you can rebuild. I always rebuild from the right to the left. So I know my constant is negative 3. Negative 7 would go with x, and positive 6 would become an x squared. So what we have here is x minus 5 times 6x squared minus 7x minus 3 equals f of x. Well, the only way to figure this out is I need to do some factoring. Okay, so 6x squared minus 7x minus 3. It's not a nice one for us, but we can do it. So I'm trying to come up with two numbers that multiply to be a negative 18. That have to be a negative 7. What two numbers that multiply to get negative 18, but have to be negative 7? So negative 9 and a positive 2. All right, so we need to be able to factor as we're working through these problems. All right, I'm just going to bring this all the way down here. So this one goes into 4 spot, 6x squared minus 9x plus 2x minus 3. In order to factor this, I can do my factoring with my groups. This one I could factor out a 3x, and so it'd be 2x minus 3. Conveniently, this one's already 2x minus 3, so really all I had to factor out was a 1, maybe a positive 1. So I have 3x plus 1 multiplied by 2x minus 3, and then I cannot forget this x minus 5 that was still a factor. So factoring 6x cubed, this big long one, into linear factors, when they tell me one of the zeros, great. Now I can build this quadratic. I still have to factor this quadratic to get two binomials. My two binomials are 3x plus 1, 2x minus 3. Okay, this is doing math. This is, I mean, there's a lot going on in here that we have to be able to continue to go with. What's that? Mason, you say something? Oh, I thought you said something. Okay. Questions on this? This is part 1 of today. 3 parts. Okay. You're not going to have as much time as normal. Okay? But there's a lot of stuff. Term's coming to an end. We got stuff to do. It's all right. All right, here we go. Rational root theorem. Okay, let's let some function p of x. Okay, so p f of x doesn't matter. I could use any variables I want. So let's let this p of x be a polynomial with integer coefficients. Integers are just numbers. They're not fractions. 2, 7, negative 3. For any polynomial, we know that there's a limited number of possible roots. And roots, again, where it's crossing the x-axis. Zeros, roots, all means the same thing. Okay? But we know our roots are going to be wherever our polynomial crosses the x-axis, where it's equal to 0. Same thing where it crosses the x-axis. Okay, so what we have is called the rational root theorem. What's rational mean again? We see rational all the time in math. What's rational mean? So we're going to talk about rational coefficients versus integer coefficients. What's the difference between a rational versus an integer coefficient? Rational just means a fraction. Okay, so instead of a coefficient being 3x squared, we could have 3/4 x squared. Our rational root theorem tells us that the integer roots will be plus minus factors of the constant in our polynomial p of x. Okay, so we have some polynomial going on. So say p of x is 3x cubed plus 2x squared plus 5x minus 3. What is my constant in that polynomial that I just created? -3. Okay, so integer roots, all I'm looking at is the factors of this -3. And so plus minus factors of it, I know 1 and 3 are my only two factors of 3. And so I'd say plus minus 1, plus minus 3. Now my rational roots will be plus or minus factors of the constant divided by factors of the leading coefficients. In my polynomial function that is made, what's the leading coefficient? Okay, it's this 3. This is the leading coefficient. Okay, so I'm creating a fraction by factors of my constant divided by factors of my leading coefficient. So we're going to get a big list going on. And just that list isn't the final answer. There's stuff we have to do with that list. Okay, so hopefully this is bringing back fond memories from Algebra 2 when you did this. All right, so let's just do kind of surface level. Let's find rational roots or possible rational roots. Okay, so list all the possible rational roots of this one. 2x cubed minus x squared plus 2x plus 5. And a lot of times they'll use a lowercase p and a lowercase q to represent each one. So the constant would be lowercase p and lowercase q. So first off, what are the factors of the constant? So plus minus 1, plus minus 5. Those are my only factors of my constant term. What are the factors of the leading coefficient? What is the leading coefficient on this one? 2. So plus minus 1, plus minus 2 are my leading coefficient factors. Therefore, the list that I'm going to create of possible roots, I have to do each of these. So my factors of my constant term. So this is plus minus 1 divided by 1. So I would just write that as 1. Plus minus 1 divided by 2, because I'm going this one divided and then this one divided. But then I also have to do 5 divided by 1, so that's just plus minus 5. And I also have to do 5 divided by 2, so plus minus 5/2. So that's my list of possible rational roots, possible zeros of this one. Okay, I know out of those 8 that I'm going to have zeros of this function. Okay, let's do it again, make sure we're comfortable with it, and then we're going to extend this problem and continue on. Yep. Okay. I'll put these on Schoology too. All right, let's do another one, but we're going to continue this problem on and finish it. So using the rational zeros theorem, list all possible rational zeros for this polynomial. So again, that lowercase p just means constant. So my factors of my constant, in this case, my constant was 4. Don't worry about this a sub 0. I should probably actually just take that out. Okay, we're just looking at factors of that constant. Well, I know I could do plus minus 1, plus minus 2, and plus minus 4 would be all of my factors of my constant. And then factors of my leading coefficient, again, my leading coefficient here is 8. So Q they like to use. So this would be plus minus 1, plus minus 2, plus minus 4, plus minus 8. Everybody comfortable how I'm getting that 1, 2, 4, 8? It's always plus minus on every single one. So therefore, possible rational zeros or rational roots, I'm going to take P divided by Q. So that's factors of my constant divided by factors of my leading coefficient. So this is where it gets kind of tedious, because you're going to take plus minus 1 divided by 1, plus minus 1 divided by plus minus 2, 1 divided by 4, 1 divided by 8. You're going to list out all of those, and you're going to keep going. So 1 divided by 1 is just 1. 1/2, 1/4, and 1/8. But now I got to keep going. So I'm going to do 2 divided by 1. So that's plus minus 2. And then plus minus 2 divided by 2 is just 1, so I don't have to list it out again. I already got that taken care of. Plus minus 2 divided by plus minus 4 would be plus minus 1/2. I already got that accounted for. I don't have to do that one again. And then plus minus 2, and then divided by plus minus 8, that gives me my 1/4, which I already have, so I don't have to write that again. So going on to the second one, all I really added was plus minus 2. Looking at 4, I have plus minus 4. Plus minus 4 divided by 2 is 2. I already have that one. 4 divided by 4 is 1. I already have that one. 4 divided by 8 is 1/2. I already have that one. So you don't have to duplicate them. You don't have to write them down again if they're already up there. So these are all possible roots. Okay, these are not saying these are the roots. These are just possibilities of what my roots could be. Now, let's take it a step further. Same problem. Okay, it's just a part B to it. Find all rational zeros and factor f of x into linear factors. So again, this same one. So f of x was 8x to the 4th. Should I write this down right? Minus 26x cubed minus 27x squared plus 11x plus 4. We're trying to break that polynomial into all of the factors of it. Okay. From here, it's trial and error. You just have to start testing your possible roots. Okay. So the first one, is 1 a factor? So you can kind of shortcut this, and I already know from those first slides, if it's a factor, if I put it in here, I'm going to get 0. Okay, so if I put 1 into here, I'm going to have 8 minus 26 minus 27 plus 11 plus 4, and rather than going through all that, I'll tell you end up with a negative 30. Okay, so I know 1 is not a factor. So 1 is not a factor. My options though are plus minus 1. So let's try negative 1. I'm going to tell you this one does work. And you can test it. If you put in negative 1 into all these x values, you'll get 0. And that's good. But that just gives you a starting point. Okay, I'm going to use that for my synthetic division. And we're actually going to put here in our press box, we would put a positive 1. All right, because we're saying is 1 a factor? Make sure I'm telling you this right. We're actually going to put in negative 1. So we're going to test out negative 1, not. So let's use our synthetic division. 8, negative 26, negative 27, 11, and 4. I know this is going to end up with 0 down here. But let's fill in all the other stuff because all that other pieces will help me determine my polynomial. Okay, bring the 8 down, end up with a negative 8. And remember, we're adding. So this becomes a negative 34. Multiply through, this becomes a positive 34. Add those up, end up with a positive 7. Negative 7. Bring that down, becomes 4. Multiply through, that becomes negative 4. And I do get 0, which is good. But again, this makes up my new polynomial. So this is my constant. So I know that's 4. This would be 7x. This would be a negative 34x squared. And this would be 8x cubed. We're trying to get it as linear factors. All I know is x plus 1 is a factor so far. So I could say x plus 1 times all of this will equal my initial polynomial that I'm working with. Okay, so we've confirmed x plus 1 is a factor. We have to keep going. This one's not done. So I said these problems can get long, can get tedious. Okay. So we've gotten to this point right here, which is what we just had on that last slide. Well, now we have to keep going and see, okay, from our list of possible rational roots, this is where we're going to try again. Okay, and for the sake of time, let's try 4 to determine if 4 is a factor. If I were to put 4 back into the original, not this one, if I were to put 4 back into the original, it does equal 0, which is a good thing. Okay, all right, so let's go use our synthetic division to break down this one. So I'd have 8, negative 34, 7, and a positive 4. Bring 8 down. 8 times 24 is 32. Add those together, get a negative 2. And a negative 8. Add those together, get negative 1. Negative 4, get 0. So again, that's what I want to happen. So now I can break this apart even more, and I can say, well, x plus 1. And I'm going to say in this one, if this is a factor, then it's really x minus 4. And then my new polynomial here, 8x squared minus 2x minus 1. So we're getting closer. Come on, stay with me. Stay with me. I'm going to make you guys stand up. Okay. Not there yet, but we're getting close. Let's factor this real quick. So negative 8, that adds up to be a negative 2. Two numbers I could have a combination of 4 and 2, I know. All right, and so I'm going to say negative 4 and positive 2. So 8x squared minus 2x minus 1, I'm going to factor with 4 spot, 8x squared minus 4x plus 2x minus 1. Do my groupings. Factor out 4x. This would be 2x minus 1. Conveniently, it's the same as here. Factored out the 1. Okay, so now my polynomial becomes f of x in factored form, x plus 1, x minus 4, 4x plus 1, 2x minus 1. So now I have all the factors of that initial polynomial that I was working with. And let's look at what these zeros would be. So the first one I know x would be a -1. The second one I know x would be a +4. 4x plus 1, that would be a -1/4. And then the last one would be +1/2. And these were all in my initial list that I had. So -1, 4, -1/4, 1/2. Using that rational root theorem got me started. Okay, so I had this big long list. I could pick one, or as soon as I find one, I can use that. Okay, but then it got us to this cubic. Okay, from this cubic, now still my list is still good. I'm not going to use -1 again. I'm going to use something else and then keep going. Okay. All right, last one. Okay. Find a polynomial function that satisfies the condition, my real zeros. So we want to create a function of degree 3 that has zeros at -3, -2, and 5. But also, they're telling me if I put in -1, I get 6 as an answer. So that has to hold true also for my polynomial. Okay. So if -3 is a 0, what's my binomial going to be? What am I going to put in here? If 3 is a 0, what's my binomial that it's going to make it up be? X plus 3. If -2 is a 0, that would be x plus 2. If 5 is a 0, that would be x minus 5. But this additional statement that f of -1 is 6 tells me that there's some a coefficient outside here. Remember, standard form ax squared plus bx plus c? That there's some a number also going on. Okay, so if it's saying that f of -1 equals 6, that's saying if I put in 6 here and I put in -1 for all my x values and solve that, that will tell me what a is. Okay, so f of -1, that -1 represents my x's, equals 6. Okay, if I were to solve all of this, I'll just do it for you, you'd end up with 1/2 equals a. Okay, if you take all those numbers, multiply them, divide them by 6, 6 is equal to a. So f of x is going to be equal to 1/2 times x plus 3 times x plus 2 times x minus 5. But we want a polynomial of degree 3. This is not degree 3. Degree 3 would be x cubed. So we have to multiply all of these 3 together to get our x cubed. And I will just tell you for sake of time, ends up being 1/2 x cubed plus 19 over 2x plus 15. And we could arrive at that simply by multiplying all 3 of these binomials together and then times by that 1/2. This a actually should be a -1/2. Change that up to a negative. And then last one. This one I'm just going to set up for you. Find a function f of degree 3. So again, we're going to have some x cubed that has 0, 4 in multiplicity of 3. Back to our stuff with multiplicities. Dayton, what's stuff with multiplicities? Okay, multiplicity of 3 means repeated zeros. So if it has a 0 at 4 and a multiplicity of 3, that means 4 is a 0 3 times. Okay, and so my function f of x would be a times x minus 4 times x minus 4 times x minus 4. That's what that multiplicity of 3 means. And so I'd have negative 24 equals a, and then I could start putting in here 2 minus 4, 2 minus 4, 2 minus 4, and I could come up with my final polynomial after I figure out what a is. In this case, a is equal to 3. And I'll tell you our final polynomial ends up being 3x cubed plus 144x minus 192. Again, after we put in that a of 3 and then multiply that x minus 4 3 times, we end up with this for a final polynomial. So you'll be given problems where they will give you the zeros and ask you to create the polynomial. You'll be doing rational root theorem where you got to find all those possible zeros and factor it into your linear factors. And in the very beginning, just that remainder theorem or the factor theorem. If we put it in, we get 0. That's good. We're going to go from there. Okay. Too much for a Monday? Yeah. Oh my goodness.